In the second part of this talk, we will review the basics of calibrations and G2 geometry, moving towards the definition of associative threefold and associative Smith maps. At the end of this section, we will explain the analogy between symplectic geometry on the one hand and G2 geometry on the other. So let's begin with the definition of a calibration. Let M be a Riemannian manifold of dimension n. A calibration on M is a K-form such that two properties hold. First, it's closed, and second, it has comass 1, meaning that for all k-planes V in the tangent space of M, alpha restricted to V is at most the volume form of V. An equivalent definition, which is maybe somewhat more intuitive, is that alpha of E1 through EK is at most 1 for all oriented orthonormal collections of k vectors in the tangent space of M. Now, let sigma k be an oriented k-dimensional submanifold in M. We'll say that sigma is calibrated by alpha if alpha restricted to sigma is the volume form of sigma. The point of these definitions is the following fundamental theorem of calibrations due to Harvey and Lawson. Let M be a Riemannian manifold of dimension n, and let alpha, a k-form, be a calibration, and let sigma be an oriented k-dimensional submanifold of M. Notice that k is the dimension of sigma, it's also the degree of the calibration form. The point is that if sigma is calibrated by alpha, then sigma is homologically volume minimizing. This is a very strong volume minimization or volume optimization condition. It implies, in particular, that sigma is a minimal submanifold. The precise definition of homologically volume minimizing is this. For every compact subdomain k in sigma, the volume of k is at most the volume of any competitor, k tilde, where k tilde is any domain having the same boundary as k and is homologous to k. Now, while I can't know for sure how Harvey and Lawson came up with these definitions in this theorem, the following might be how they did it. If you look at the proof for why complex submanifolds in Cn are volume minimizing, that was known some 30 years prior to Harvey and Lawson's work. If you look at that proof and you try to take that proof and turn it into a definition, what you will end up with are exactly these definitions here of calibration and calibrated submanifold. So this is sort of an example of turning a theorem into a definition, as it were. So here's maybe the fundamental non-trivial example of a calibration. In R2n, thought of as Cn, the standard symplectic form omega 0, that's a 2 form, given by dx1 wedge dx2 up to dx2n minus 1 wedge dx2n, that is a calibration. It is closed and has comass 1. Its calibrated submanifolds, by definition, are the surfaces sigma 2, for which omega 0 restricted to sigma is the volume form of sigma. Okay, one can show that the surfaces satisfying this condition are precisely the complex curves in Cn. So, in particular, the complex curves in Cn are homologically area minimizing. Okay, so here's a generalization of example A. This is sort of a nonlinear curved version. Okay, so let's let M omega j be an almost Kähler manifold. Okay, this is just the setting we saw earlier, wherein omega is a symplectic form, it's a non-degenerate 2 form that's closed, and j is a compatible almost complex structure. Okay, we say it's almost Kähler just because j is not required to be integrable, per se. Note that, in particular, just by virtue of having a symplectic form, there is, at each point x in M, there's a linear isomorphism L from Txm to R2n that identifies omega, this should be omega at x, with omega 0. To say that another way, there is a frame, E1 through E2n at x, for which omega at x looks like omega 0. It's E1 wedge E2 up to E2n minus 1 wedge E2n. So, it follows that omega has comass 1, and the symplectic form omega is a calibration. Its calibrated submanifolds, by definition, are those surfaces with the condition that omega restricted to sigma is the volume form, and again, these are precisely the complex curves in M2n. Okay, so notice that example A is the flat version of example A prime. Okay, but the example that's relevant to our talk is this one. So let's let O denote the octonions. That's basically a copy of R8 with a certain product operation, and equip it with its standard inner product, the ordinary inner product on R8. Okay, split the octonions into the real octonions plus the imaginary octonions, where the real octonions, that's just the span of the number 1, so that's just a line, and the imaginary octonions is the orthogonal complement, so that's a copy of R7 inside R8. And let's consider the imaginary octonions, this copy of R7, a little more closely. The octonions endow MO with some very interesting geometric structure. For example, there is the so-called 7-dimensional vector cross product, which I'm going to call Q0, on R7. Okay, so Q0, or just denoted x cross y, it's just the commutator. It's 1/2 xy minus yx, where these products, this product here refers to the product in the octonions. Okay, one can check that this is in fact alternating, and it is well defined. It lives genuinely in the imaginary octonions. Okay, now this vector cross product can be recast as a 3 form, essentially just by lowering an index and using the metric. So that's this right here. The associative 3 form is defined by the inner product of x cross y with z, or in the Q notation, it's Q0 of xy comma z, inner product. Okay, so this is basically equivalent to the vector cross product using the metric. Okay, so if you write phi0 in standard coordinates, you get this somewhat awful expression. Phi0 is dx123 plus dx145, etc., where we're writing dxijk as this shorthand for the wedges. Okay, and these numbers are not arbitrary. These are this is the octonionic multiplication table, as it were. If you think of the octonions as being spanned by 1 and E1, E2, E3 up to E7, this says, for example, that E2 times E4 is E6. And the reason we're mentioning this, of course, is because phi0 is a calibration. It is closed and has comass 1. Okay, we'll call its calibrated submanifolds, we'll give that a name, we'll call them the associative threefolds. Okay, so this is a class of 3-dimensional submanifolds in R7, and it's defined by the calibrated condition. Phi0 restricted to sigma is the volume form of sigma. Okay, now in the previous slide we had a linear example of Cn, and then we generalized it to a nonlinear setting of almost Kähler manifolds. We'd like to do the same thing here. We have an example taking place in flat Euclidean space, and we'd like to generalize this setting of MO, a copy of R7, to manifolds in general. That consideration leads to the definition of a G2 structure. So let's let M be a smooth 7 manifold. In the flat case, that's R7, of course. Okay, a G2 structure on M7 is a 3-form phi, such that any of the following equivalent conditions hold. So one is that for each x in M, there's an isomorphism L from TXM to R7, and this isomorphism identifies phi0, the form on the previous slide, with phi at x. So phi looks like the associative 3 form on R7. Okay, to say that another way, at each point you can find a frame, E1 through E7 at x, such that phi at x, well, looks like the associative 3 form. A more intrinsic condition that's equivalent is the following. For each x in M, the symmetric bilinear form B phi defined here, this is a symmetric bilinear form that inputs vectors and outputs a 7 form on the 7 manifold M. This symmetric bilinear form is definite. Okay, but the main point here is that what a G2 structure does intuitively is at each point of M, it identifies the tangent space of M with a copy of the imaginary octonions in such a way that phi at x is basically phi0. So this is sort of a, we're saying that each tangent space has the structure of the imaginary octonions in this sense. Okay, whether a 7 manifold admits a G2 structure is a purely topological question that can be answered with characteristic classes. Okay, this is kind of like which even-dimensional manifolds admit an almost complex structure. It's somewhat analogous to that. And it's known, not too hard to show, that M admits a G2 structure if and only if M is orientable and spin. Okay, now something about G2 geometry which is very different from the symplectic setting is this. A G2 structure phi induces a canonical Riemannian metric and orientation. Right, now that's very different from the symplectic setting because if you have a symplectic manifold, you do not automatically get a Riemannian metric. You have to also choose an almost complex structure that's compatible. Here, the G2 structure alone is enough to give you this canonical Riemannian metric. This is a consequence of the fact that G2 is contained in SO7, whereas the symplectic group, for example, is not contained in SO, N. Anyway, the way you get this canonical Riemannian metric and volume form is via this first formula. And then once you know that, then it follows as a consequence that the volume form can be recovered as 1/7 phi wedge star phi, for example. And just as in the case of the flat R7, a G2 structure can be regarded equivalently once you have this metric as a vector cross product. Okay, so you have a vector cross product on each tangent space. This is basically the 7-dimensional cross product, if you like, and it's defined by, in this case, raising an index from phi. And as before, we'll denote it Q when convenient, or sometimes we'll use the cross product symbol. Just some warnings. First of all, the map phi to h phi is not injective, and that means, more concretely, that different G2 structures may induce the same Riemannian metric, and there are certainly examples of this. Moreover, the map that sends phi to h phi is highly nonlinear. We'll get back to that point in a minute. And moreover, the Hodge star is, of course, determined by the metric and the volume form, but the point is that those depend nonlinearly on phi. Okay, so in a way, a somewhat deeper concept is that of a G2 manifold, right? Just as an almost complex structure, you are really primarily interested in the case when it's integrable. This is somehow the analog of that in a certain sense. Okay, so a G2 manifold is a 7-manifold M7 with a G2 structure phi that is both closed and co-closed, meaning that the 3 form itself is closed and co-closed. Okay, I should mention that this is a system of nonlinear first-order PDE. It appears to be linear, but as I said before, the Hodge star depends nonlinearly on phi. So this right here is a nonlinear system, whereas this one is, of course, linear. Note that, for example, the flat R7 with its associative 3 form phi 0, that is a G2 manifold. Its holonomy group is just the identity. I mention this because there's, I think, maybe a misconception that G2 manifolds are precisely the 7 manifolds with G2 holonomy, and clearly that's not true by the example of flat R7. However, there is a relationship between G2 manifolds and G2 holonomy, and here it is. It's given by a theorem of Fernandez and Gray. Let M7 be orientable in spin. If you have a G2 structure that is closed and co-closed, then the induced metric has holonomy contained in G2. Conversely, if you have any Riemannian metric on a 7-manifold that's orientable in spin, if its holonomy is contained in G2, then in fact it must arise in this way. It must be induced from a G2 structure that is closed and co-closed. Finally, I'll mention, although it's not directly relevant to this talk, that every G2 manifold is Ricci flat. Okay, these are very important examples of Ricci flat manifolds in odd dimensions. Right? In general, it's extremely difficult to construct examples of compact Ricci flat manifolds that are not flat. And as far as I know, we in fact only have examples in the trivial dimensions 1, 3, and well, of course in 1 and 3 they're automatically flat. The only examples we know are these right here in dimension 7. So just as when you have an almost complex structure, there is then a distinguished class of submanifolds. Similarly, when you have a G2 structure on your 7-manifold, there is again a distinguished class of submanifolds. The starting point for this observation is the following fact. Every G2 structure, phi, has comass 1 with respect to its induced metric. That's half the definition of being a calibration, so of course, in particular, if phi is closed, then phi is a calibration. So once again, the calibrated threefolds in M7, the three-dimensional submanifolds that are calibrated with respect to phi, we'll call those the associative threefolds. Okay, so this finally is the nonlinear generalization. This would be example B prime, if you will. This is the generalization of example B that we saw earlier. So we'll say that sigma is an associative threefold if it's calibrated by phi, meaning that this condition holds. An equivalent condition that's maybe somewhat geometrically enlightening is that if V and W belong to the tangent space of sigma, then their cross product does too. So the tangent spaces are somehow closed under the cross product operation. That's equivalent. Another equivalent condition is this: every tangent space to sigma has a basis that associates. So a basis xyz such that xy times z is x times yz. Here, this is the product of octonions. We're thinking of the tangent space to M as a copy of the imaginary octonions, and that's what we mean by this product here. And so geometrically, we can think of sort of the flat model of sigma 3, of an associative sigma 3 and M7. We're really saying that the tangent space to sigma sits inside the tangent space to M, somehow in the same way that the imaginary quaternions sit inside the imaginary octonions. This is the model of what's happening here on the linear level. Okay, so there are some very basic examples of associatives in R7 to keep in mind that show just kind of how complicated and rich the class of associative threefolds really is. So if you have a complex curve C in R6 and you cross that complex curve with a line, you get an associative in R7. So associatives in R7 are somehow at least as complicated as complex curves in R6. Moreover, if you have a special Lagrangian in R6, and you just, let's call it L, and you just include L into R7 in the usual way, then L is an associative in R7. So associatives in R7 are also somehow more complicated than special Lagrangians in R6. A final construction I'll mention is that if you have a complex curve in the 6th sphere, we're thinking of 6th sphere in the usual way, the unit sphere in R7, and it has its ordinary non-integrable, almost complex structure, J, then the cone over a complex curve will be an associative in R7 minus the origin. So these cones are models for conical singularities of associatives in R7. Okay, so hopefully this gives some intuition and also some understanding of just how complicated this class can be. Okay, but we're interested not so much in submanifolds, but rather in maps which parameterize these submanifolds. Okay, so these will be the associative Smith maps. So our domain will be an oriented conformal 3 manifold. Okay, we'll denote that as sigma 3, and we'll denote the orientation in conformal class by a star, the Hodge star, where we're thinking of this Hodge star as the Hodge star on 2 vectors rather than on 2 forms. The reason for this will be clear in a minute. But one way to think about this Hodge star geometrically is in terms of the ordinary 3-dimensional cross product that's familiar to us. Right, E1 cross E2 is E3. Our target will be a 7-manifold with a G2 structure. Okay, so phi is a 3 form, that's a G2 structure, and remember that it gives us a cross product called Q on the tangent spaces. So finally, our definition: a map U from sigma 3 to M7 is an associative Smith map if this first order PDE right here holds. This is the associative Smith equation. Okay, what is this saying? So both sides of this equation take as inputs 2 vectors. So just for concreteness, let's plug into both sides v wedge w, a decomposable 2 vector. Then the left-hand side becomes duv cross duw. The right-hand side is this strange factor times du of v cross w. So what this says is that associative Smith maps, these are the maps which you might say conformally intertwine these 2 cross products, the 7-dimensional cross product on the left and the 3-dimensional cross product on the right. Okay, they're somehow the same sort of under du up to this weird factor. This factor is included so that this equation becomes conformally invariant. Okay, I should mention that this factor can be 1. That happens precisely when U is an isometric immersion. Okay, so that certainly can happen. Now, we've phrased this in terms of the cross products Q and the Hodge star. However, there's an equivalent definition in terms of forms, okay, which makes sense because cross products are somehow dual to forms in a way. So you can equivalently say that a map U from sigma 3 to, of course, this should be M7, is associative Smith if and only if it is weakly conformal and this equation here holds. Okay, U pulls back phi to be this function times the volume form of sigma. Okay, and you can see already kind of the similarity between this equation and the J-holomorphic map equation. Why one should believe that this is directly the analog will be made a little bit more clear in the next section, where we explain a generalization of both this and the J-holomorphic map equation. But at the moment, let's summarize what we've done in terms of an analogy. So the analogy between almost Kähler manifolds and G2 manifolds is this. On an almost Kähler manifold, you have a calibration given by a 2 form, and you can lower an index to get an operator called J on the tangent spaces. In a G2 manifold, you have this 3 form, okay, and that's somehow the fundamental object, and again, you can recast it using the metric as a cross product, Q. So Q is, in the G2 world, playing the role of J, and phi is playing the role of omega. And in both cases, you have a distinguished class of submanifolds, and these distinguished classes of submanifolds are defined by really similar-looking conditions, right? Clearly, the condition of being associative is very similar to the condition to being a complex curve. There's even these equivalent characterizations in terms of the forms. And again, in this analogy, the J-holomorphic maps, they're defined by this first-order PDE system, the Cauchy-Riemann equations, and the associative Smith maps are defined by this analogous PDE system. The only maybe unusual thing that's maybe a little odd is this factor here. But again, this factor is there for a good reason. It's to make this equation conformally invariant. Okay, so in the next and final part of this talk, we will place everything in a even more general context, that of general Smith maps. And in that context, we will state Smith's theorems stating the geometric properties of Smith maps, and we will also state our own results on the analytic aspects of associative Smith maps in particular.